Le Chatelier's principle. In so many words, the idea is that you can adjust equilibrium by messing with the concentration, the temperature, or the pressure. Most of it is common sense. Let's have a look at some examples. Suppose we're taking some starting materials and turning them into products, and we note that the reaction is endothermic. What would happen if we added some reactant? Well, it should shift things to the right. The analogy that works for me is it's like stoking the fire. It's like adding wood to the fire. It's going to push things to the right. Let's add some product. That would be like adding carbon dioxide or water to a fire. That is not going to help. That is going to shift it to the left. We are quenching the fire. Let's add some heat to the reaction. Well, you know, this is endothermic. I mean, it needs heat, right? So that should help things out. And in fact, this would shift it to the right because it needs it. Note that the opposite is also true. If it's an exothermic reaction, heating it will shift it in the opposite direction. That's a tough one. Let's pressurize it. What would happen? Simple rule, it always favors the fewer numbers of moles. Here, 4 dip molecules combine to form 1. So we're going from 4 to 1. Pressurizing should help. It always has favors the fewer number of moles. It would go in the opposite direction if we had a greater number of molecules on the right. Those are the simple rules for Le Chatelier's principle. Let's apply them. Imagine you had the reaction of nitrogen monoxide combining with oxygen to form nitrogen dioxide. It's an endothermic process. If we add nitrogen monoxide, that's a reactant, should shift it to the right. Nitrogen dioxide, product, shift it to the left. Oxygen, reactant, shift it to the right. Remove it, we'll shift it to the left. Now, usually I just think about what would happen if I added it, and then I switch it, right? Remove NO2, well, that will open up to product, shift it to the right. Remove oxygen, that opens up reactant, shift it to the left. Increase the pressure, 3 to 2, yeah, we're good. Increase the temperature, does it need it? It does, it's endothermic, shifts it to the right. Decrease the pressure. Well, if I increase the pressure, it went to the right, so decreasing to the left. And finally, decrease the temperature. Well, increasing the temperature to the right, so decreasing to the left. Finally, and boy, is this the most important thing about equilibrium, after all that mumbo-jumbo, the best way to drive a reaction to completion is to destroy it. How can you destroy it? Remove a product as it's formed. If it takes the products combining with each other to go back to reactant, simply have one of them precipitate out or get collected in some way, and you have no equilibrium at all, and suddenly your 60% yield is now 99%. So remove the product as it's formed. Chemists have come up with all sorts of creative ways to do that, and that is probably the most important thing in practical terms about chemical equilibrium.